Okay, so we left off discussing the delta G, which is the change in free energy. So, and that equals to delta H minus T delta S. And the idea here is that your spontaneous reactions have a negative delta G. They give off free energy. There's a free energy change to do work. And that what is determining whether or not something is spontaneous is the enthalpy and the change in entropy. So when we look at those values, we had four thermodynamic scenarios, and some of them were temperature dependent, others were not. So we saw that if delta H is exothermic and the system becomes more random, that delta G is always negative. We also saw that if we had a endothermic process where the entropy was decreasing, it was always positive delta G, so never spontaneous. And then we had the two that were temp dependent. And so let's keep going with this thought and kind of expand on the idea of what delta G is going to tell us. Okay. So let's calculate delta H, delta S, and delta G. We have these thermodynamic functions data from the back of the textbook. So we have the molar enthalpies of formation and the molar entropies. And this is the easy part, right? We're going to just do products minus reactants, taking into account the coefficients. So for the enthalpy, we take 2 times the enthalpy of formation of SO3 minus 2 times the enthalpy of formation of SO2 minus 0. The way your book does this is a little bit different than I like to do it, which was they distribute the negative sign. Okay, so take a look at that. I tend to add them and just keep them in parentheses. They distribute the negative. So we end up with an exothermic process at negative 198 kilojoules. Okay, so that's exothermic. Okay, next, for the entropy factor, same type thing. We've been practicing now this a lot. We end up with a negative 187. So what I want you to do is to think about which category we are in, to really think about what this is telling us. So take a minute. You can pause me. Okay, so really what we have here is an exothermic process where the entropy is decreasing. And if we look at the big picture, so the enthalpy wants to make this spontaneous. The entropy, though, because it's subtracting a negative value, is working against the enthalpy. So this is trying to make it spontaneous. This one's not. So this category would be temperature dependent. And so we have to see, is the temperature of 298 enough to allow for this to happen spontaneously? So let's see. Plugging in to our Gibbs-Helmholtz equation, and this was assuming 298. the delta G was in fact negative. So it was spontaneous at this particular temperature. Now we can calculate that crossover temp. So there's the enthalpy, and then here's our entropy value. I'm converting it to kilojoules. So if we go ahead and calculate that, that's 198 divided by 0.187. See if I did that right. Yeah, that's a really big temp. Okay, so very high temperature. So anything below that temp is going to mean it's spontaneous. So 298 is well below that. So we know that it'll be spontaneous. So remember to think of it this way, that in this process, what is driving this reaction is the enthalpy. It's enthalpy driven because that is very negative. Okay, so anything below the 1059 would be a temperature at which it would happen spontaneously. Now, one of the things that you can also do is you don't always have to calculate. So this is that was the long route actually to finding delta G of reaction, because you can more easily find delta G using the delta G's of formation. And these are also in the back of the book. And basically what it is that the delta G's of formation are the changes in free energy that accompanies the formation of 1 mole of its substance from its constituent elements. And so any delta G of formation of an element is 0 because it's in its standard state already. So we can just use the tables from the back to go directly to delta G. So for example, if we have this reaction and we want to find delta G of reaction, here's the delta G's of formation. And so we'll just take products minus reactants once again. And I can go ahead and do that here. So we're going to take 2 moles times, where's the CO2, negative 394. These are in kilojoules. Okay, that's our product, right? Plus 4 moles times negative 229 minus 2 times negative 163 plus 3 times 0. Okay, and just as that FYI, again, what your book does is it distributes this negative. So it's going to show it this as negative, and if this was a number, it'd show it that as negative. I don't do it that way. I add them and then just subtract that quantity. And either way, we should get a delta G of reaction of negative 1378 kilojoules. So for sure, this is a spontaneous process under standard conditions, which is the 298. Now, what I want you to think about, and this is a very important slide, it seems very boring, but it's super important. When delta G is negative, that means that a reaction is product favored. And as we head into the next section then, if a reaction is product favored, let's think about the previous chapters we've done. The equilibrium lies to the right. K equilibrium is very large. All of the things that we talked about in discussing the magnitude of Kc or Ka or whatever the reaction is, if delta G is very negative and has a big value, then K equilibrium is very large, meaning that this reaction is thermodynamically favorable, product favored. And so where are we headed is kind of coming full circle to understand how delta G's relate to K equilibrium. Okay, now as we think about this, let me click. There's going to be reactions that are not spontaneous. So the opposite is true, that delta G naught is positive, and that means that those are reactant favored. Okay, and those reactant favored ones, the K equilibrium is much less than 1. Now, if we look back and we think about some of the processes that we've looked at over this last semester, we've had processes that have a very small K equilibrium. Okay, as we move into the battery chapter, we're going to be looking at some real extremes where there's some batteries will give us a huge amount of energy and are very much product favored, but the reverse process of trying to recharge those batteries requires an outside external energy. And that's where they are not spontaneous and delta G is positive. Okay, one of the things that I also mentioned to you, so this one here is the idea of a current. The other thing I mentioned to you was in biochemistry. In biochemistry, we talk about delta G all the time because in each process, in processes like glycolysis or Krebs cycle, a biochemist will take a look at the delta G values and try to understand how those unfavorable processes are pushed forward. And one of the main ways in biochemistry that that's achieved is by coupling a process that has a positive delta G is coupled to a negative delta G. So the example that I gave you guys was muscle contraction requires ATP, because ATP, that has a very negative delta G when that molecule splits apart, and then that drives an unfavorable process. So here's the current, this electrolytic cell. This is in our next chapter, so chapter 18. So we're going to talk more about that. Electromagnetic radiation could be used. I actually did mention this in trying to make ozone from oxygen. And then conversion of carbon dioxide to glucose through photosynthesis. That's another, that is started by absorbing sunlight in the form of radiation. Or sunlight is a form of radiation. Okay, so what I want you to think about now is, before we start this slide, is to think about the fact that delta G naught is from the tables in the back of the book. And those solutions, or anything from the back, is standard conditions, where if you have a gas, it's at 1 atmosphere. A solution is at 1 molar. But we don't always run reactions like that. And so we could talk about free energy, or change in free energy, in non-standard conditions. And there is an equation that relates delta G, non-standard, meaning that your solution may not be 1 molar, your gas may not be 1 atmosphere. And there's an equation that relates the two. Which is delta G equals delta G naught plus RT ln Q. Now, to make sense of this, what I want to do is talk to you about a very spontaneous reaction and kind of put this into perspective. And it's kind of going towards the next chapter, but that's good, I think. So that's the reaction of zinc reacting with copper 2 ion. You did a lot of this last semester in single replacement. Okay, if you drop a piece of zinc into a solution of copper 2, they will spontaneously react. All right, now what this would mean is that you wouldn't always start off with 1 molar of copper 2 and 1 molar of zinc. You may not be at that standard condition. And so the idea would be this, is that initially in a reaction, you would have zinc with copper, right? Reactants only. And they'd start to react. And so if I think about where we're at in the process, we're not at standard initially. So how would I describe where we were at? Where we'd be at is we talk about our friend Q, taking a picture of where we are at on the way to reaching equilibrium. And so Q would be products over reactants, which would just be zinc ion over copper 2. And if we are initially there, then what you want to think about is that you would have a whole bunch of copper 2, because that's a reactant. This would make Q very small. And then now going back up into our equation over there, if Q is very tiny, you can plug in some numbers if you want. I'm trying to get a different color here. If Q is small, delta G is very negative. More negative than the standard conditions. And so what this leads us to think about is when we set up a reaction, that initially, if we have this reactants only in a very spontaneous reaction, what delta G is really giving us is an indication of the maximum amount of work that this process can do. And initially, I like to think of this kind of as a process falling downwards, that up here, you are at the most negative that you can be. That's your maximum amount of work in this spontaneous process. Okay, so that's initially. Then, as the product accumulates, you reach the point where Q equals 1 because you start getting enough zinc ion and it's going to equal the amount of copper. At that point, you are not at equilibrium. Q equals 1, and if I come over to my equation, if Q equals 1, what's ln of 1? 0. So this term drops out. So that whole term drops out. This is where you have delta G standard conditions. The reaction progresses, keeps going, and now Q, you start building a product, right? Because it's progressing. And what does that mean? Is that there's more zinc ion, and that makes Q bigger. And what does that do for delta G? It's still negative, but delta G is less negative. So this is more negative, more work. As this process continues, you have less and less work. And then ultimately, this number starts getting so big, Q gets so big that eventually, in this very spontaneous process, Q eventually will equal K and you're at equilibrium. At that point, what's going to happen is that so here's our equation. We can substitute and write delta G naught plus RT ln K, because now you're at equilibrium. But at equilibrium, this term has gotten so big that it matches the delta G naught value. And what happens there is, but it's actually big, but what ends up happening is that this amount of work ends up being 0 because you reach equilibrium. So at this point, delta G goes to 0. And that means that our process has no more work. Okay, and so what will end up happening if we actually plugged in a really large number, we'll see here in a minute, that this term is same magnitude but opposite sign of the delta G naught. And so what happens is that delta G goes to 0 and you reach equilibrium. Okay, so that's what non-standard conditions mean, is that you're not at delta G naught where Q equals 1. You could be more work or you could be less free energy to do work. It just depends where you're at in this whole process. So like everything, hopefully you remember Q's like a snapshot. And if we were to know Q, we'd know where we'd be at. So up here at the top, Q is less than 1. here Q is greater than 1, and then here Q at equilibrium equals K. It's super big. Okay, so with this in mind, well, here's the reaction. So Q is the reaction quotient. This is temp. This is our universal gas constant. Free energy change at 1 atmosphere standard conditions. Okay, so the other thing that comes up is that then if we're at equilibrium, delta G is 0, non-standard. Okay, so 0 equals delta G naught plus RT ln K. Delta G naught equals negative RT ln K. And this is a really exciting point for us because it brings together all these chapters we've done. What this is saying is that if K is much greater than 1, delta G is negative, product favored, and spontaneous. Solving for K will equal E to the negative delta G over RT. So these are two really important equations. Now, what I want you to think about is that what this means is we can find K equilibrium if we know delta G naught. And we can find delta G naught using the thermodynamic values. But it should all come together that product favored reactions with very large K equilibriums will have delta G's that are negative, meaning they're spontaneous, they're product favored. Okay, so let's take a look at how big these values for K can get in a product favored spontaneous reaction. Okay, we'll come back to that slide. I like this one, but let's come back. So here's a reaction of iron with oxygen to produce iron 3 oxide. So this is really thinking about corrosion or rusting of a nail. Now, what do you know about a nail that's rusting is that we should say is going to happen spontaneously. Now, not all spontaneous processes are fast. So there's thermodynamically favored versus kinetically favored. So in other words, sometimes they go hand in hand. A spontaneous reaction can be really fast, but they're not always linked. So the rusting of a nail can be very slow, but still spontaneous. Okay, I don't want to do these anymore. So products minus reactants. If you want to practice, go ahead and do both delta H and delta S, and then find delta G. Stop me and then double check your answers. Okay, so here's ultimately our delta G from that process. And so this is very, very exergonic, which is a term for delta G being negative. That term's used a lot in biology, biochemistry. So releases a lot of free energy. Look at that, 10 to the 6. Okay, super product favored, right? But let's now plug that number into delta G equals negative RT ln K, and then solve for K as E to the negative delta G naught RT. And let's see if your calculator can handle those kinds of numbers. I doubt it. Try it. Sometimes it says no thank you, overflow, because it's just too big. And remember, the R is the 8.314 value. Did it overflow your calculator? Probably. And oops, I have to erase now. I don't know if I can erase. Oh yeah, I can. I thought it was on the next slide. So, okay, you're going to go ahead. And solve for, let's see, how did they set this up? They do it a little bit different. L and K, okay, and let's see what they did on the next slide. Oh, there we go. So K equals E to 601. So that would have been the same thing that I was telling you guys to do, except that if you try to plug into your calculator, it's not going to want to do that. So K will equal E to the negative delta G over RT. And then with that incredibly negative delta G value, this would have been this value here, which your calculator won't be able to handle. But what I want you to think about is how incredibly large that K equilibrium is. And so the resting of a nail is very product favored. It's just slow. So kinetics is not included in this discussion. So this is wow. So what I want you to think about is in our time together this semester, we started our path together with reversible reactions where K equilibrium was around 1. And if K equilibrium is around 1, then delta G is around 0. Those are these wonderful reversible reactions that we started our semester with. Oh my goodness, I don't remember what chapter it was, but the first equilibrium chapter that seems a million miles away. Okay, then we have scenarios where K is much greater than 1. Product favored, like the rusting of this nail or iron. Combustions. Precipitations. Dissolving of some salts in water. Those are all and then the batteries we're going to be looking at in the next chapter. Those are all product favored, and delta G's for those will be very negative. Strong acids. Remember, the K's were so big we didn't even reference them. Strong bases. And then we had reactions where delta G's were positive. We didn't realize it. Those would be where K values are very, very, very small. So insoluble salts, KSPs, that would have been when you did your lab on calcium carbonate. So, in the All About Carbonate, you looked at KSP values that were very tiny. You had your weak acids. And on a majorly extreme side, we're going to see later, will be what are called electrolytic cells. These would be processes like taking water and trying to break it down into its elements, things that require that outside source of that current. Okay, so keep in mind though that, and so I'm going to go back to this one nice little chart. Oh. Oh no, it's making me, I don't want to hit end show because there was a nice chart. Oh my goodness. I hope you're laughing at me right now. I'm too scared to hit that button. Here we go. This is where I was trying to get to. This is what I drew up on that number line, that when you have K that's around 1, then you have those truly reversible reactions, and delta G will be around 0. When K is very big, you have product favored. And then when K is less than 1, you have reactant favored. And the delta G is positive. And so this is a really, really important understanding of the relationship between delta G naught and K. And then those guys are linked through your new favorite equation, which is this one, and then solving for K, e to the negative delta G naught over RT. And I think that's it. Oh, okay. These last couple slides, this is just to get you to think about the temperature dependence of K. And this, I'm not going to have any questions on. So this is not for lecture, but this is where in your lab, the thermo lab, you know how we're finding enthalpy and entropy for the dissolving of potassium nitrate. So this is just one little section at the end of this chapter. So I just wanted to include it so that you can see where the equation that we're using for lab is coming from, but I won't ask it on lecture. Okay, so really what I want you to think about is the big picture of equilibrium constant and delta G. So one other thing, oops, see if I end show, it doesn't let me.